Solution concentration. Okay, this is sort of a little leap, but we'll come back to the stoichiometry. So let's think about putting salt, this table salt, in a glass of water. You stir it up. It seems to disappear, right? Or become a liquid. It just all, you had two things and now you have one thing. You get a homogeneous mixture. The salt is still in there. If you taste the water, it's very obvious, ooh, there's salt in there. If you take the water that has the salt dissolved in it and you heat it and boil away the water, the salt will remain. Okay? So it didn't disappear. They just mixed and became a uniform homogeneous mixture. Well, in chemistry, we call a homogeneous mixture a solution. So a solution has two parts, the solvent and the solute. So the solvent is the part that there's more of, okay? So in our example here, if you took a teaspoon of salt and put it into a glass of water, there's a lot more water, and so we would call that the solvent. They can occasionally be a little tricky to identify which is the solvent or the solute. Another clue is that the solvent keeps its state. So here the salt was a solid and the water was a liquid. And when we mixed them together, we have a liquid. So that also suggests that water is the solvent. The solute is the part of the solution, the part of the mixture that is present in lesser amount. The solute may change its state. So the salt here started out as a solid, now it's a liquid. It doesn't always do that, but it might. And you can have more than one solute in a solution, because you could also put some sugar into the water, and you could put some food coloring in the water, and you could put some cinnamon in there. I mean, my kids do stuff like that, and they make a horrible mess in the kitchen, right? You can put lots of different things in there. So there's one solvent, there's one or more solutes. Solutions are mixtures, and mixtures have variable composition. You could put 1 teaspoon of salt in, you could put 3 teaspoons of salt in the water, right? It's still a solution. It's not a compound where you have a fixed proportion. Pure substances have constant composition. These mixtures can have variable composition. So in order to describe a solution accurately, we have to specify how much of the solute is in there. Is this super salty water, or is it just barely salty? Pure substances, we can just use a single name because it's always going to be the same. But with a solution, we have to specify the relative amounts of solute and solvent. So we have qualitative descriptions. These include words like dilute and concentrated. So a dilute solution would have a relatively small amount of solute compared to the solvent, and a concentrated solution will have more, a larger amount. So here's a concentrated solution. There's a lot of these little blue, I don't know what they are, little blue atoms or something in there. And this dilute solution, there's not as many. So these are relative terms. This one is dilute relative to that one. But we often need a more quantitative way of expressing the concentration. So molarity is the unit that we use the most in chemistry. So molarity, and the abbreviation is a capital M. It is important to make that a capital M, not a lowercase m, because a lowercase m is meters, and a capital M is molarity. And when you're writing this out by hand, it can, well, first you have to pick a pen before you can write anything. So, is that a capital M or a lowercase m? As a capital M. See, whatever you said, it was going to be wrong. When it's just an M, it's hard to tell, right? Unless you're very careful and make your M's real pointy like that. I don't have time for that. So one thing we often do is if it's a capital M, we underline it. If it's a lowercase m, we don't. And so that way we don't have to go just by the size of the M. So molarity is defined this way. It's the amount of solute in moles divided by the volume of the entire solution in liters. So we'll sometimes make that a little shorter and say capital M equals moles per liter. Remember that MOL is the abbreviation for mole. Capital M is abbreviation for molarity, moles per liter, and lowercase m is meter. If we want to have abbreviations and not have to write out all the words, then we have to use them precisely. This is an illustration of how you might make a solution that has a specified concentration. So the task here would be to make a 1 molar sodium chloride solution. 1 molar means 1 mole per liter of solution. So we could use a 1 liter volumetric flask, which is good for measuring a specific volume of liquid, and we could add 1 mole of sodium chloride. So we'd have to figure out how much it weighs and weigh it out. So that'd be 58.44 grams of sodium chloride. Then we would add water. We would dissolve this, make sure that all the solid got dissolved, and then we would fill this up. This has a mark on the neck, just like volumetric pipettes do. And so you'd fill it up with the liquid until the bottom of the meniscus is right at the mark. Then you would stopper it, and you'd have to invert it back and forth many times to get it to mix thoroughly. And that's one way to make a 1 molar sodium chloride solution. So let's do a couple examples. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. Well, they ask us to calculate the molarity. So this is where we need an equation. So molarity equals moles of solute per liter of solution. Do we have either of those? Did they give us moles of solute? No. Did they give us liters of solution? Yeah, they did. So they told us it was 2.50 liters of solution. So that's good, but they're going to make us calculate how many moles of sodium nitrate. So 45.4 grams of sodium nitrate. And we want to convert that into moles of sodium nitrate. So we'll be dividing by grams of sodium nitrate so the units work out. So where do we get the number? We have to calculate a molar mass, right? So for this compound, as sodium is 22.99. And we have 1 nitrogen, 14.01, and 3 oxygens, 16.00. So 22.99 plus 14.01 plus 3 times 16 equals. My calculator says 85. How many sig figs should that have? Well, here I've got these guys that I'm dealing with. All of my molar masses had 4 sig figs, so my total molar mass for the compound should have 4 significant figures. So I really should put 00 here, grams per mole. It doesn't happen very often where it comes out to be exactly 85. It's like you go to the grocery store and it comes out to be exactly $100, and you're like, maybe I should buy a lottery ticket today. Don't, you won't win. So here's 85.00 grams down there. So we do the math, and we come out with 0.534. Well, those aren't very good. 534. The 45.4 had 3 significant figures. And so here I need 3, and then I'm going to write down the next 2 digits, and that's moles of sodium nitrate. So that's what I need in the numerator. 0.534, yeah, I meant to do that. 1 moles. So I take the 0.53411, I divide by 2.5. This also should have 3 sig figs. I'm getting 0.213, and the next 2 digits are 64. When I round that, I'm going to get 0.214. And then the units, you can write this as moles per liter, or you can write it as capital M. Capital M means moles per liter. So this is the molarity of that solution. If we're reading it, we'd say it's 0.214 molar sodium nitrate. Nothing to do with teeth. Any questions? We've learned how to convert grams to moles before. We've learned how to calculate molar masses before. Here's a new equation. It's not very tricky, but we have to put all these pieces together. Okay, so it's a lot of building blocks, and you have to put them together in the right order. We can use molarity as a conversion factor. It's moles per liter, and as we learned in just learning about word problems, when you've given lots of different numbers and units, if it's got a per in the unit, then it's probably going to be a conversion factor. So we can use molarity as a conversion factor. So if we have a 0.5 molar sodium chloride solution, that means there's 0.500 moles of sodium chloride per liter of solution. So we can use this to convert from liters of solution to moles. Or we can turn it upside down, like other conversion factors, and use it to convert moles of sodium chloride to liters of solution. So if we know one, we can find the other using the molarity. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? We can approach this as a dimensional analysis problem. So let's write down our units, our numbers. So we've got 1.55 liters of the solution. And we've got 0.758 capital M. So capital M is a great abbreviation. You're typing on the computer, it's really easy to do. But when we look at it here, we don't recognize that that's our conversion factor. So when you write it out, don't write the capital M. Write what it means, moles per liter. So this is 0.758 moles per liter. Now this looks like a conversion factor. And so which of these numbers am I probably going to start with? The liter. This has a per in it, moles per liter. That's my conversion factor. This is where I'm starting. And the question is, how many grams of sucrose? So how many grams of sucrose? Can I go directly from liters of solution to grams of sucrose? No, I don't have that conversion factor. What can I get using this one? Using the molarity, I can go from liters of solution to what? Moles. Moles of sucrose. Can I go from moles of sucrose to grams of sucrose? Sure, that's the molar mass. This is moles of sucrose, the solute, per liter of solution. So I figured out my path. That's the hard part. So 1.55 liters. And I'm going to convert that to moles of sucrose. Yeah, I think sucrose is easier than the formula. And now I'm going to convert that to grams of sucrose. So put moles down here. So those cancel. And I've got liters down here. So this is moles of sucrose per liter. Well, that happens to be the molarity right side up. The units tell me that. So 0.758 goes with moles, so I write it with the moles, 758. And that's per 1 liter. And then here I need the molar mass of sucrose. So we have to calculate that. 12 times the mass of carbon plus 22 times the mass of hydrogen plus 11 times the mass of oxygen. $342.296. Now my shortcut for sig figs on these molar masses is if you're using molar masses here that are rounded to 4, then this would have 4. Doesn't hurt to write down all of it. That would be grams per mole for sucrose. So here I have grams on the top and moles on the bottom. So I want to put the 342.296 on the top, and that's per 1 mole. So 1.55 times 0.758 times 342.296. Smallest number of sig figs is 3, so 402.16. And we round that, we get 402 grams of sucrose. Any questions? Yeah. The 0.758? Oh. Anybody else get this? Yeah. Did you use these exact molar 12.01, 1.008, and 16? And what did you get? 406? Well, it's possible that you just got a number in there. Funny. Oh, well, I don't know what I did there, but now I've got 5,026. So that's okay. Yeah. I think you just must have made a little mistake in your calculation. Any other questions? So we often have chemical solutions that are more concentrated than what we need to actually use in the lab. It's a little bit like going to the grocery store and buying concentrated frozen orange juice, right? You're not going to drink it in that form, but it's convenient because it takes up less space, right? So we often store concentrated solutions. We call these stock solutions. We have them in stock, and we store them in the stock room, right? So when we need a more dilute solution, just like with the orange juice, we just add more solvent and dilute it until we get the right concentration. When that happens, the amount of solute doesn't change. So you think about orange juice, and you squeeze the goopy stuff into a pitcher, and then you fill the can with water and dump it in 3 times. Now, the amount of orange goodness that's in the pitcher is the same amount as was originally in the can. We don't get any more, we don't get any less. All we're doing is we're adding water, and so we're making it less concentrated, because if you try to eat it straight out of the can, it's just way too sweet, right? You have to dilute it so you can drink it. When we take a stock solution and add more solvent to it, the amount of solute doesn't change. So if you have the moles of solute in solution 1, the more concentrated, is equal to the moles of solute in solution 2. So only the volume changes. So because of this, we can write an equation like this. M1V1 equals M2V2. The molarity of the first solution times the volume of the first solution equals the molarity of the second solution times the volume of the second solution. And if we look at this, molarity is moles per liter. And we're multiplying that by a volume in liters. The liters cancel out. And so over here, we've got moles per liter times liter, and the liters cancel out. The number of moles don't change. Just the volume changes. So this is an equation you need to know. M1V1 equals M2V2. It's for dilutions only. Here's how you might dilute a solution. So here we have, we're using 0.150 liters of a 10 molar stock solution. We're putting it into a flask that's larger, and we're diluting with water, so we get a total volume of 3 liters. So the number of moles here is the molarity, 10 moles per liter, times the volume in liters, 0.150. So that's 1.5 moles of solute. In the diluted solution, now the concentration here is 0.5. Yeah, I'm sorry, I was comparing that to that. Never mind. 0.5, brain fart. Now we have 0.5 moles per liter, but we have a larger volume, 3 liters, and so we do that calculation. We still have 1.5 moles of the solute, the calcium chloride. So let's practice. What volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? So these problems will typically have 3 numbers given. So let's pull those out and figure out what they are. So we've got 100.0 milliliters, and we've got 5.00. I'm going to write that as moles per liter instead of capital M. And then I've got 0.750 moles per liter. That's a little messy there. So let's label these. Well, this first one is a volume, right? And this is a molarity. And this is a molarity. We're diluting something, and so we've got this equation, M1V1 equals M2V2. The way a straightforward problem works is they give you 3 of those numbers, you have to find the 4th. So we've identified we have 1 volume and we have 2 molarities. We need to put them together correctly. Number 1 does not have to be the more concentrated. Number 2 doesn't have to be the more concentrated, but you have to get the volume with the correct molarity, right? So that's where the words help us out. 100 milliliters of 5 molar. These 2 go together. Column 1, column 2, whatever you want. I'm going to call them 1. So 100 milliliters, volume 1, of 5 molar. That's molarity 1. Those go together, so this molarity must be molarity 2, and then what I'm solving for is volume 2. Any questions about that? So if I'm solving for V2, I want to rearrange this equation So I'm going to divide both sides by M2. The M2's cancel out. So volume 2 equals molarity 1 times volume 1 divided by molarity 2. So I can put the numbers in. Molarity 1 is 5.00 moles per liter. Volume 1 is 100.0 milliliters. And volume molarity 2 is 0.750 moles per liter. Let's check out what's going on with the units. I have moles per liter in the numerator and moles per liter in the denominator. The moles are going to cancel, the liters are going to cancel. I have a unit of milliliter left. I don't necessarily have to convert this volume to liters before I put it into the equation. You can, but then in this problem, you're going to have to convert it back to milliliters at the end. So we do the math here. 5 times 100 divided by 0.75. So volume 2 should have 3 sig figs. 666.66. That's kind of scary. Milliliters. So when we round that, we get 667 milliliters. It's a good idea with a dilution equation, dilution problem, to look at it and ask yourself, does this make sense? So I'm taking 100 milliliters of this more concentrated, and I'm going to make it less concentrated. That means the volume has to be bigger, right? This volume is bigger, so that's a good sign. The most common problem is people will get these upside down, and then the volume will get smaller, and that's just not going to work. Any other questions? Now that we have molarity as a conversion factor, we can add this as a variation to our stoichiometry problems. So molarity relates moles of solute to liters of solution. So if we're dealing with solutions, which we often do when we're doing chemical reactions, instead of looking at the mass of the solute, we can look at the volume. And the volume is easy to measure. You just pour it into a graduated cylinder, measure it. The molarity allows us to convert that to moles. So we can go from volume to moles, and then to volume. So this is a variation on grams to moles to moles to grams. So previously we had done grams to moles to grams. So now we have two options here. You can do volume to moles to grams, volume to moles to volume, grams to moles to, etc. Lots of variations. But the overall idea is the same. There's moles in the middle. So what volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So molarities, those are moles per liter. The volumes you will usually encounter in these problems are milliliters, because milliliters is a more reasonable size for which to do experiments. You know, if you're doing this on a commercial scale, it would be liters or kiloliters or something. But in the chemistry lab, we use milliliters. So we need to just get used to that. So let's organize the information using the equation. So I've got some information about the nitric acid, 0.150 moles per liter. Write it as a fraction, not capital M. And then I've got 35.7 milliliters of that. And they also give me a molarity, 0.108 moles per liter. What is the question? What volume in milliliters of nitric acid? So question mark, and the unit requested is milliliters. So we learned grams to moles to moles to grams, but this time we don't have grams at the beginning and the end. Grams to moles to moles to grams. Moles per liter is a conversion factor. Milliliter is what we're starting with. So instead of grams here, we've got milliliters. And then the question is, how many milliliters? So instead of grams at the end, we're going to milliliters at the end. Okay with that? Is this a limiting reactant problem? No. No, it isn't. We're given information about one reactant, we're given a concentration of the other reactant, and then we're asked for a volume. We want to know, we've got this much sodium carbonate, how much nitric acid will completely react with that? So it's not a limiting reactant problem. So I'm going to start with this single unit, the 35.7 milliliters of the sodium carbonate. And then I'm going to go to moles of sodium carbonate. And then I'm going to go to moles of the other thing, the nitric acid. And then instead of going to grams, I'm going to go to milliliters. Well, I'll do liters. I'll explain why in just a minute. So I'm starting with milliliters. These molarities are in moles per liter, but then I want milliliters at the end. So I can treat this milli like I did the kilo in the other problems, where I don't cancel it out. So here's the milli, and I'm not going to cancel that out. I'm just going to let it sit there. There's other ways to do this, but again, it's what I've decided to do this time. So I cancel the liters of sodium carbonate. I go to moles. This is my mole ratio. Here, moles per liter, those are the units on the molarity. So at the end, I've crossed out everything except liters and milli. So my ending unit will be milliliters. Everybody okay with that? If you don't like that, you can convert this from milliliters to liters, then go through here and get liters and convert back to milliliters. That's fine. So the numbers here, we'll find that these problems are actually less work because we don't have to calculate molar masses. So here in the middle, we need our mole ratio from the balanced chemical equation. 1 mole of sodium carbonate reacts with 2 moles of nitric acid. So we get those in there. Here, instead of calculating grams per mole, we have been given the concentration, 0.108 moles per liter. So I have 0.108 moles of sodium carbonate per liter of solution. And that's right. And then over here, I need the molarity of the nitric acid, which was also given, 0.15 moles per liter. Here, moles is in the denominator, so the number has to go down there too. So in 1 liter of that solution, there's 0.150 moles. So my calculator is giving me this number. I should have 3 significant figures, and the unit will be milliliters. So I'll round that for a final answer to 51.4 milliliters of nitric acid. Any questions? We end up doing a lot of milliliter to liter conversions. And it's really helpful if you can do those in your head. So let's just think about that for a minute. If I wanted to convert this to liters, right, I can write it all out, milliliters on the bottom, liters on the top. Milli means 10 to the minus 3. So I've got 1 times 10 to the minus 3 up there, and I end up with 0.0357 liters. That's not an 8, that's a 3. This conversion involves moving the decimal point 3 places. If you can remember which direction to move it, you can do it in your head. So you have to move it in the correct direction. So we've had a little bit of experience in lab now, right? How much is a milliliter of liquid? Little tiny, right? How much is a liter of liquid? It's half of a 2-liter soda bottle, right? So could 35 milliliters be 35,700 liters? No, that would be silly, right? It's like saying that, 3 feet, like saying that 24 inches is 2,000 feet. It's getting it backwards, right? So if you think about liters and milliliters, we know the relative sizes. Milliliter is a smaller unit. It should have the larger number. Liter is a larger unit. It should have the smaller number. That can help you remember which way to move it. If you keep getting it backwards, then either do it this way or write the whole calculation out. It's silly to get the wrong answer because you've got this glitch in your head and you keep moving the decimal point in the wrong direction. Any questions?